Anyways, so the story is getting deeper. We started by discussing these things called propositions, which I said were like the atoms of the math world. And as long as you ignore the fact that actually atoms are not the smallest thing in the universe. But, for general purposes, they are indivisible, like prime numbers, right? And as far as integers go. So a proposition could be true or false, and that was nice, but we need a way to connect them to create different signals. So we have the unary operators, the binary operators, and then from those, and along with the conditional and biconditionals, we could create even more complex propositions, culminating in what we called predicate, predicates and quantified statements. So in order for us to be able to do mathematics or to do computer science, create algorithms, to do cybersecurity in a theoretical point of view, which we'll say from like number theoretic type of aspect, we need a foundation upon which we can always know when something is correct or not. So we can know if a theorem is true or not true. And so we looked at arguments, valid arguments, modus ponens, modus tonens, and we know they were valid because whenever we created the truth table for any combination of inputs, we always got the same output, which was true. So an axiomatic system, so now we're taking it to the next level. We're creating essentially like a micro universe in which we can create theories. We can define the properties of some object, create theories around it, and then use propositional logic as a foundation, use that methodology to prove the theorems that we suspect are true and deduce from the axioms. Okay. So before I go into what an axiomatic system is, let me just remind you, what is an axiom? Does anyone know that? An axiom. What is an axiom? Is it a body spray? No, that's X. Sorry, bad joke. Okay. These are axioms. An axiom is something that we can assume is true without proof. It's sort of like, okay, you're telling me that we have to prove everything, but if we say that's true, we have to have a starting point. There's a really famous book called Euclid's Elements. And Euclid was a Greek mathematician, maybe geometer, some people might say, number theorist. And Euclid had this idea of like collecting all of the mathematics of his time, all of the mathematics that was being used, that people knew how to use for engineering, for architecture, for purposes of taxing agricultural lands, for military use. He wanted to collect all these things that people were using and put them on a rigorous foundation. So in other words, to prove that these things were true. And he had to start with axioms. And sometimes it's going to get annoying, but there are like three words for the same thing oftentimes. And so there's another word for an axiom, which you might call a postulate. But you can think of it as a starting point. For example, Euclid had to start somewhere in order to prove all of the theories that he proved. And one of the places that he started with respect to geometry was with the definition of a point. So if I were to ask you what is a point, what would you say? take a few moments and come up with an answer, put it in the chat or tell me here. What is a point? I like that answer. Yeah. A line with zero length. Okay. Well, if it has zero length, that is a length. So let's maybe refine that. You're on the right track, I think. I don't know. It's because you're using length that makes me suspicious. A distinct location or object. Okay, what else? You guys can see what they're saying if you want. Mary, what is a point? No? What about you, Brendan? What is a point? There's no right answer. It's just, I mean, there is one, but not that you have to have it. You're not supposed to know it. A line with zero magnitude. If you well, okay, what if I just say it's a sphere with zero volume? Is that the same thing, Timothy? So, okay, so what Euclid said, so yeah, what you're getting at, I think, is it's a zero-dimensional object. That's what technically we would say, because a line is one-dimensional, but a point has no dimension. Yeah, it has no magnitude. But if I have so Euclid described a point. He said it's that which has no breadth, width, or height or depth or something, anyways, that described a volume. So basically a dimensionless object. But if you happen to have 2 points, then between every 2 points, there is a line. And now we have one dimension. So we go from like 0 dimensions to 1 dimension, you connect two lines together, now you have 2 dimensions. And you can create like all of geometry based on the axiom of having a definition for what a point is. So yeah, an axiom is something that we assume is true without proof. Basically a starting point. We have to all agree like that this is a line, that is a point, that is a square. And then once we've agreed on those things, we can go ahead and develop some other theorems. Okay, good. Good choices there. So an axiomatic system then is a finite sequence of propositions. So everybody knows, do you know what a sequence is? It's an ordered list of items. So the thing that makes it a sequence is that there's a specific order to a specific order in which the items appear and the fact that it's a list. And each of the elements in the sequence have an index. So like this one would be index 1. Or if you're making a sequence in Python, it might be index 0. That's a joke. Okay. So index 1, index 2, and then up to index n. So an axiomatic system is a finite sequence of propositions A1, A2, up to AN, which are called axioms. And these propositions, since they're axioms, are considered to be true without proof. Okay, so let's go on to the next. So what is a proof in an axiomatic system? An axiomatic system can take several different forms, and we're going to see a couple of different axiomatic systems by the end of this class. But the point of having these systems is that it gives us this framework in which we can apply our propositional logic. So we have this idea of proof in an axiomatic system. In other words, a way for us to know whether or not a proposition P is true. So here's our definition of a proof. It is a proof of a proposition P within an axiomatic system is a finite sequence of propositions. Okay. So these propositions are not axioms. They're just propositions that are in the axiomatic system. And we say Q1, Q2, up to Qm. These are all propositions such that whenever these are all simultaneously true or conjoined with our AND operator, they create a conditional that guarantees the conclusion will be P is true. Okay, so that is a proof. You've got this sequence of propositions that when all joined with an AND guarantee this conclusion P. So that's the first part of the definition, but there are some rules to what these propositions could be. So the rules for what these propositions could be, and it says such that for any J, so J just means like if I select a random index, all right, between 1 and the last one. So for any of these propositions between the first one and the last one, that proposition could be from the list of axioms. So one of the ways we can prove something in an axiomatic system is by using one of the axioms in our proof, right? So because the axioms are always true. The jth step of the proof is a tautology. So we get to like Q1, Q2, Q3, and then we see that we have P or not P. So Q3 or not Q4, that would be the tautology, right? Those are the first two rules. The third rule is modus ponens. So if there exists two propositions that when conjoined guarantee a third proposition. Okay, so right now these are like very symbolically complicated looking things, but it's going to make sense if you review this. Let's go back to the start. So we have an axiomatic system. What is it? It's a list of axioms. And axioms are propositions that are always true. So these propositions, these propositions that are axioms create what I would say is the minimal structure for the axiomatic system. So a good example of an axiomatic system that we'll see later on, but I kind of want to jump to it now, is the idea of a metric space. A metric space is a way to define distance, okay? So if you think about what is required for something to be a distance, that kind of gives you the idea of what an axiom might be. So what do you have to have in order for something to be a distance? What do you think? If I want to define a distance, what would I always guarantee must be true? Let's see if you can answer some of these. Suppose I have the distance from A to B. What must be true about the distance from B to A? Yeah, exactly right. If you have something that's called distance, the distance from one point A to the point B had better be the same as the distance from B to A. If not, that is not a distance. What else? What else could we say about distance? Can you have a negative distance? Yeah, you can't have negative distance. Great. Yeah, it has to always be positive. So, like, there's one more axiom that makes something a distance, but just those two alone, you kind of get the idea that if one of those axioms were missing, then you wouldn't be able to calculate a distance, right? Because you can't have negative distance, and it has to be true that the distance from A to B is the same as from B to A. So these are axioms, and if one of them is missing, then we no longer have that particular structure or object. Okay, so the list of axioms gives us the minimal structure, but from that list of axioms, we're able to make deductions or theorems about what also might be true. For example, we talked about the number 0 in the integers, right? And we said that if I add any number to 0, what happens? So if I add any integer to 0, what do I get? If I add any number to 0, what will I get? I'll get that same integer back, right? Like, so like 5, yeah, 5 plus 0 will be 0. M plus 0 will be 0. And so that is an example of an axiom. If we have, so the integers form something, it's got a special name called a, hey, did I do that or did somebody else do that? Oh, okay. I didn't do that. The integers form a special kind of structure called a group under certain conditions, under a binary operation. We're going to talk about groups too. One of the axioms of a group is that it has an identity element. The identity element is the element that when you use the binary operation with that element, it does nothing. It just gives you back that same element. So 2 plus 0 equals 2. 0 is our identity element. So that's an axiom. If we have a group, it must have a 0. The more technical term being identity element. But that is just an axiom. From that axiom, we could also make a theorem that that 0 must be unique, which in fact we proved in a previous class, right? We showed that if there was more than one identity element, actually it was just the same one. So that's an example of like how you can start with axioms and develop a theorem and then use this system of logic to prove that theorem true. All right. So in our axioms, we have a proof. So what is the proof then? It's this finite sequence of propositions. And this makes it also useful to be able to feed it into a machine, basically. If I have a finite sequence of propositions that must be either 1 or 0, then I could feed that into a model and it can determine if I have a correct proof or not. So if Q1 and Q2 up to Qm are all true, then it must guarantee this proposition P. So that is a proof. And then what are the rules of the propositions? Either these propositions are the axioms or they combine to form a tautology, or, well, we'll see more about something like that in a moment. No, I don't want to do that. Or you have two of them together that create a modus ponens type situation where when you conjoin them, they are the premise of a conditional statement that leads to another proposition further on in the sequence. Okay, let me go forward. So if P can be proven from the axiomatic system, A1 up to AN, then we write down that A1 up to AN, and then this symbol right here, P. So can prove P. P is provable. So this definition, again, it allows for easy recognition of a proof, which means that if we can easily understand what a proof is, we know when it's not true, or at least we can allow a program to determine that. Another thing is any tautology occurring in the axioms can be removed from the list without impairing the structure of the axiomatic system. So if you have a tautology in your axioms, then you have a redundancy essentially. definition, the consistency of an axiomatic system. So what does that mean? An axiomatic system is called consistent if there exists a proposition Q that cannot be proven from the axioms. Now, this is a little bit strange and it gets a little bit weird here because we're saying that the axiomatic system is consistent only if there are propositions in the axiomatic system that cannot be proven from the axioms. That sounds like a bummer. Like at first, like, what do you mean? There's things, if I have a consistent axiomatic system, then there are going to be things that I could never prove in the system. Has anybody ever heard of the Riemann hypothesis? This is the idea that the prime numbers lay on a line, a complex plane, like I think it's 1/2 or something. I don't know. But the idea is that a lot of people think that this is something that you can't prove. You can find that if they can find any number of primes are on that line, but you can't prove that it's true for every prime number. And there are other theorems like that where you can keep finding examples of it, but you can't write up a systematically correct proof. And it could be the case that because the system is consistent, it's impossible to do that. Okay, so why do we need to have a consistent axiomatic system? Here's why. So if we had an axiomatic system that contained contradictory propositions, so like if I have S and then not S up here, then by modus ponens, I could have S and not S implies Q. So basically, if I have contradictory propositions, then I will always have the possibility of having a false premise in a conditional. And we all know that anytime a conditional has a false premise, it's true. So this would lead to a contradiction, which means that any statement proven in a contradictory, any statement can be proven if contradictory axioms exist. So we must exclude contradictions, right? Because if you have two things that are contradictions, then you can always create a conditional that's true, right? So that means you have to have things that cannot be proven. There must exist things that cannot be proven. Okay, so here is a theorem. And this is kind of it's very abstract, so take a moment and let's think about it. Well, I guess I have all the answers here on the same thing, so never mind. So the theorem is that the system of propositional logic is consistent. Okay, so what does that mean? It means that there are theorems, there are propositions within propositional logic that cannot be proven using the axioms of the system. So the proof is very simple. It's that propositional logic has no axioms. So this is sort of a vacuous proof, you would say. Propositional logic has no axioms. It has the idea of a proposition, which can be true or false. It has binary operators, has unary operators, but it has no axioms. And so therefore, you can never prove any theorem from the axiomatic system from the axioms of propositional logic, since it has no axioms, which therefore qualifies, it is the definition of consistent, a consistent axiomatic system. What is a consistent axiomatic system? It is a system, where did it go? a system where there exists a proposition Q that cannot be proven from the axioms. So since propositional logic has no axioms, then definitely there's a proposition Q that cannot be proven from axioms that don't exist, right? So there it is. So our system of propositional logic is consistent. Okay. I'm not going to go into this. You can look into that if you want. Gödel's incompleteness theorem. I'm not going to get into that. Let's go to our first example of an axiomatic system. So here I've got a metric space. A metric space is a mathematical object, and it's used in so many different things, from data science, machine learning, cybersecurity. What else? Any kind of thing where you're looking at finding distances, right? Statistics, multivariate statistics. So a metric space is a mathematical structure in which we can define some kind of a notion of distance. What do we got here? No axioms, because axioms are considered to be always true. Well, there's just no, yeah, there are no axioms whatsoever. Yeah, propositions are not axioms because of that's true. Good point. Propositions aren't axioms. Binary operators aren't axioms. So the chat said, the system of propositional logic has no axioms because axioms are considered to always be true while propositions are binary. Yeah. So there are no axioms. And so therefore, vacuously, it's consistent. Good point. Very good point. So metric space, axiomatic system. All right. So first we define what it is to be a metric space. And if you are missing any of these properties, then you're not a matrix space. So here's the definition. A metric space is a set X together with a function called a metric or distance. And here's how we read these symbols. We say that the function D is, you can either say it's a function or you can say it's a mapping. And right here, we're saying we're taking the pairs of where the first coordinate comes from this X and the second coordinate comes from this X. So basically, you're taking the two coordinates from the same set, but yeah. So we're taking two points from each of these sets, and it's going to return a real number. Okay, so that's what this means. So that satisfies the following property. So let me go over this again. So you have some function D, which takes in an ordered pair, and it could be it depends on what dimension we're in, but for the most part, we'll say an ordered pair. And then it returns a real number, which represents the distance from one point to the other. Okay, and it satisfies the following properties for all x, y, and z in X. So for all x, y, z elements of X. First of all, we have non-negativity, which is that the distance from X to Y should be greater than or equal to 0. And if the distance from X to Y is 0, then that means that X is the same as Y. So the only time you can get a distance of 0 is if I go from A to B, but A is the same thing as B. So if I don't move at all. Next, we have symmetry, which you guys mentioned earlier. If I have the distance from X to Y, that definitely must be the same as the distance from Y to X. And then we have a very important axiom. And actually, in the metric space, it's an axiom, but in order for us to be able to show whether or not a distance function creates a metric space with some set, we have to first prove the triangle inequality is true for real numbers. So for a metric space, this is an axiom. And when we want to check to see, is this distance, is this scheme of calculating a distance considered a metric space or considered a metric in a metric space, we have to be able to um, prove the triangle inequality first. So the triangle inequality is an axiom of the metric space. So what does it say? If I have the distance between any 2 points, x and z, it should always be less than or equal to the distance of x to a third point plus that same point to z. And we're going to get really in depth on that. So another example of an axiomatic system is called a group. So the definition and properties of a group. So what is a group? A group is a set we call G, and this like the letter you use, it's kind of like up to you, but historically people use the letter G for group, probably because of the word group. So you've got a set G together with a binary operation, and we call the binary operation generically star. So this binary operation, it doesn't have to be addition or multiplication, although it could be. It just is any binary operation that takes two of the elements of G and creates a third element that is actually still in G. So the way that we read this is that star is a binary operation that takes a pair from G and then outputs a single element of G. So the binary operator does something to them to create just one. So like addition is probably the simplest idea, right? If I have like 5 and 0, then I output 5. So the following properties must hold for all elements of G for A, B, C, and G closure, which means that if I take two elements from G and then I create a third element using that binary operator, that element is still in the set G. Okay. So again, I want to point out we're talking very abstractly here, but we will see examples of all these. So just if your head is spinning, if you're like, what is the G, what is the A, what is the B, we will get to some concrete examples. Right now, we're talking about minimal structures, axiomatic systems. So, okay, so if I use the binary operator on the elements of G, that the result of that will still be in G. Associativity, this means that the order in which I combine things with the binary operator doesn't actually matter. So I can combine A and B, and then after that combine with C, or I could combine B and C, and then after the result of that is created, combine it with A. Every group has an identity element, which means that there's some element in G so that when I take any element A in that group and I use the binary operator on that A and identity element, I will get A. One thing to notice here about a group is that groups are not necessarily commutative. They don't have to be commutative, meaning like we are used to commutativity in our systems of numbers. For example, 5 plus 3 is the same as 3 plus 5, right? But in a group, that isn't necessary. It's not one of the minimal structures. You can have a group that has commutativity, and if you do, then it's called an abelian group. I'll spell it. So they don't have to be commutative, but if they are, then they're called abelian groups named after Hans Abel. Groups, before I keep going about axioms of groups have a really interesting history, namely because of one mathematical character named Galois. Has anybody heard of Galois before? French, I think he was French, a French mathematician. So Galois was like a 20-something-year-old mathematician. Let me see, when was he alive? Back in the day, a long time ago, back in the day, which would have been, what does back in the day mean? 1811. Okay. So Galois lived from 1811 to 1832. You might say, hey, that's not very long. Yeah, it's not. Because uh, division not allowed. What do you mean? We don't even know what division is right now. We're just talking about a binary operation. So yeah. Yeah, don't so like we're just speaking in general. Like this is how the binary operation has to behave. So Galois was a French mathematician who lived from 1811 to 1832, and the reason I guess he was some kind of a prodigy, but the reason he only lived like 21 years was because he also was really interested in gambling and dueling, which was a thing back in France in the 1900s. Or would it be the 18th, the 19th century, aka 1800s? So he somehow he got in a, a some kind of a confrontation that ended up with a duel, saying, "Okay, you're gonna at high noon meet me here, and we're gonna have a duel." And so the night before, he went to some tavern and wrote down all of the math that he could think of, which became modern, basically group theory or Galois theory. And then the next day had the duel, and that was the end of him. So back then, mathematics was a lot more dangerous, I suppose. So there's the identity element, and then there's an inverse element. Uh, and Timothy, you said like division is not allowed. What if I were to tell you that division doesn't even actually exist? There's only multiplication and addition. What if I'd said that? Would you believe that? So the inverse element is the other requirement for there to be a group. If something is a group, all of its elements must have an inverse, which means that for every element in the group, there's another element that when combined with that binary operation give us the identity element. So the identity element basically guarantees the existence of inverses. You can't have one without the other. All right. So another example is a field. Now, you've probably been working with fields all your life because that is what the real numbers are. We can say the real numbers are a complete ordered field. And a field is a set F. So it doesn't have to be numbers, but it's a set F equipped with two binary operations. And here I'm just calling them plus and multiplication, but they don't actually have to be. Notice again, no division. You know you've done division, but now you're realizing it doesn't exist. So the following properties hold. Number one, it has to be closed. Not everything is closed. Not every set can be. It's not true that if you take any particular set and you apply a binary operator to them, that you will always get another element of that set. Um, uh, if you did use like division, let's say you did use division, right? Then if you were to take the integers and combine them under that binary operation, you would not get an integer. So that would be an example of something that's not closed. You have associativity, which again, for either of these two operations, the order in which you pair them doesn't matter. Commutativity, this is in addition to a group. So you could see like a group has fewer structural requirements than a field, right? It turns out you can do more things with a field than you can with a group. So groups are commutative. A plus B is B plus A. And also for the other binary operator. But also groups have identity elements for both binary operators, and they also have inverses for both binary operators. The last property of a group sorry, did I say group? I was meant to say field. I'm talking about fields now. The last property of a field is that the binary operators and how do they interact with each other. This is called distributivity. So if I have A times the sum B plus C, I can either add the B, I could combine the B and the C with the addition operator and then multiply A, or I can distribute A into this parenthesis and then add them together after. Okay, so let's see, what time do we have here? So that is the beginning. And so what is the point of these things? Like, what are we doing with them? Our goal is to develop proofs and proving methods. Okay, so let me write down. There we go. So let's get into that. And what I'm going to do is look at some of these axioms and look at, there we go, whether or not something satisfies our definition or not. Okay. So let me change my modality here because I'll have to go to the board to do this. Where is that at? Where are the controls? They're there. Okay. So I'm going to stop the share and then go over here. And we can get rid of this. As you'll see exactly what I'm writing on. Okay. Can you all on Zoom see that board? It looks slightly, why does it look like that? I don't know, maybe if I zoom in, that will end that problem. Okay. So what I want to do is, we're interested in discussing proofs and proving methods. So the first thing I want to do is, I guess this is it. Let's move over a little bit more. I'm just going to list some of the proving methods that we're going to be discussing. Okay, so we know what a proof is from the definition from earlier. And we know what an axiomatic system is. And we've seen some examples. So the first type of proof is called a direct proof. And we use a direct proof in general whenever we have enough information in our hypothesis to reach a conclusion. Let me zoom in a little bit. The next type of proof, overall, so actually, a sort of a subset of this would be like axiom checking, or also something called element chasing. And this element chasing is mostly for sets. We'll talk about that. Then you have your indirect proofs, where it's impossible or too difficult to prove something directly. Then we can use something called proof by contrapositive, because we know that the contrapositive is logically equivalent to the conditional. But a contrapositive really is you rewrite your argument in the contrapositive and then just proceed with the direct proof. So it's indirect because we rewrite it as a contrapositive first. The next one is called contradiction, which has the name reductio ad absurdum, which means reduced to the absurd. So in a proof by contradiction, we start off by assuming that the conclusion is false, and then proceed from there to see if that holds, like what actually would happen. And typically we end up with something called a contradiction that contradicts our original assumptions. So after indirect proofs, I guess actually I should probably put this here. Direct proofs. We also have proofs by cases. Proof by cases. So like you're going to enumerate all of the possibilities. This is also sometimes called proof by exhaustion. So you like use every possibility. That's going to be a direct proof. And then we have something called induction. And an induction is a proof on a subset of a structure that's sequential, essentially. And we have two types of induction that we're going to discuss. We have weak induction, and then we have strong induction. And you're like, well, why do we even need weak induction if we can have strong induction? Well, because we don't always need the hypothesis that comes in strong induction, but there are sometimes we do need it. So we've got direct proofs. Whenever your hypothesis contains enough information to reach your conclusion, which basically means you're enumerating the definitions of the objects in your argument. Indirect proof, where you try to do a direct proof and you end up with nonsense, so you try a different method. And induction, which is a way to prove that something is true on a set of things that are sequential, like the natural numbers or the integers, or things that you can label with the natural numbers, things that you can count. Okay, so those are the main proving techniques we're going to look at. And now let's look at an example. So let's draw a line here. A direct proof. And like I said, what is the definition of a direct proof? When the hypothesis contains enough information to prove the conclusion. Okay. So we're going to look at we're gonna have to use a lot of new notation. I'll explain it to you as we do. So my first sort of new definition is with respect to divisibility. So divisibility of, we'll say, how about integers? So remember integers, what does this symbol mean? Let me write it up here. This means that we're talking about the natural numbers and their additive inverses, if you like it like that. Okay, so not only do I have the numbers 0 through infinity, but I also have their additive inverses. But no fractions, no decimals. So when I talk about divisibility of integers, what I mean is that I write it like this. M divides n. So we use this line right here. And then I say IFF. What does IFF mean? Yes, good. M divides n if and only if there exists some other integer k. So if and only if, and I'm going to use our notation, there exists a k integer in Z, s dot t, what does that mean? Such that, this one's easier. So m divides n, that's the line means, m divides n if and only if there exists an integer k such that this letter n, this number n, is equal to m times k. That's how we define divisibility. So I'll give you an example. Does 5 divide 10? What do you think? Does 5 divide 10? So if it helps you, just think of like an arrow going this way. Like the 5 is going into the 10. Right? So definitely 5 divides 10, right? Because 10 is equal to 2 times 5. But I would say like 5 does not divide 9 because B/C, because 9 does not equal K. So let me write it like this. 5 does not, just draw a line through it, divide 9 because negation, there does not exist a K integer such that 9 is equal to 5 times K. Is that true? Is there any integer that I can multiply to 5 and get 9? There's not. There's not. Right? So that means 5 does not divide 9. Okay. So that definition I used to show us our first direct proof. And we have a theorem. So my theorem is this. I'll say for all integers. And you know what? Let's just, we'll leave it with, we'll just stick with positive integers. This will work for other integers too, but I don't want to mess with them. So I'm just going to say for all positive integers, A and B, here's my theorem. If, well, let me write down so I want to write this, let me make this clear. We're in a math class, right? But we're using complete sentences, and we have to use complete sentences. We have to use narration in between our mathematical parts, which is, I guess it's all mathematical parts, but you'll see what I mean. So Here's my theorem. For all a, b in positive integers, if a divides b, well, you know what? I forgot it. I need one more letter. I need a c. For all a, b, and c in z, if a divides b and b divides c, then what is my conclusion? Then a divides c. Okay, so now why are we proving this? Like you kind of get an idea of what it might mean, right? We want to prove something because we want to show that it's true for every one of those types of elements, for every one of those objects. So we want to prove that this is true for every positive integer. And you can't prove that by just showing like 100, 200, 300, or even a billion examples. You have to replace your numbers with letters and use propositional logic as a foundation to create propositions, a sequence of propositions that forces this conclusion, or that whose premise guarantees this conclusion. So here is my conditional. You see I have if P and Q, then R, or whatever. We're not going to go granular. We're keeping it at the English level now. So now I said this is an example of a direct proof, which means that there's enough information here to prove it directly. So the first step of your proof is to incorporate your hypotheses from your theorem. So we're allowed to assume that this is true, and we're allowed to assume the hypothesis is true. And then based on that, we need to show the conclusion will follow. So maybe I should put a comma there. So here's my proof. I'm going to say let, and you're always letting things be what they want to be or do what they want to do. So we're going to say let a, b, and c be positive integers. Okay. And we also need to incorporate this part of the hypothesis. A divides b, and I don't want to write and again, so I'm just going to put a comma. B divides c. So there's all I've done is just incorporate what is given in the theorem, and I want to use it to prove this. And how do I do it? In a direct proof, I just say, what does it mean that A divides B? We just write down, like, what's the definition of this thing? So I can say, if A divides B, then what does that mean? There exists some integer k such that B is equal to A times k. Okay, now let's talk about this one that we can assume is true. If B divides C, what does that mean? Then there exists, let's use a different letter like integer, such that, so comma, comma, such that C equals B times N. Okay. So what are we trying to prove? We're trying to prove that A divides C. So right now we have A divides B means that B equals A times K, right? And B divides C means that C equals B times N. But you see that we have B in terms of A just by writing out what this divisibility means here. So then I can say, based on what we have here without any additional information, I can say this says, so this is like a transition couple of words, right? This says that what? It says that C equals B times n, but b is equal to a times k, which is to say that a times these two integers k times n equals c. Now, k times n is an integer. So in our proofs, we're allowed to assume that integers are closed. Some things that you come across in a proof, you won't know are true, and you'll have to prove that in order to prove your proof. You'll have to prove a subproof, which is called a corollary or a lemma sometimes. So in this case, we know that an integer times an integer is an integer. And so here I have, let me write it like this, c equals a times k times n. So c is equal to a times some integer. And what does that mean? Oh, wait. What does that mean? Look at your definitions. Are you guys silent in here? On the if you can answer me in 1 minute, we'll end early. And it has to be right. What does c equals? It's not fair. This isn't about fair. This is math. Fair. What does that mean? I'm often glad life's not fair. I don't know. Maybe it is. Maybe it isn't. I'm just a mere mortal. Okay. Go back to your definition of divisibility. No, I'm not asking what c being an integer means. I'm asking what does it mean that c equals a times some integer? That is the crux of the issue here. So we said, look back at the definition of divisibility. M divides m in if and only if there exists some integer k such that m times n equals k. And what are we trying to prove here? This, right? We're trying to prove that a divides c. Have we done it? No. Not 0 or 1. A divide a is 1? What do you mean? Okay, look at this with me. Let's do like this. What does it mean for m to divide n? M divides n means what? There's some integer that when I multiply it to m, I get n. Just like this. 5 divides 10 means 10 is equal to 2 times 5, right? So here, I'm trying to prove that a divides c. So what does it mean that a divides c? It means that there's some integer that when multiplied to a gives us c. So we have it here. This is literally the definition of divisibility of a being a number that divides c. Okay? So you might have to watch this more than once. It's okay. So what does that mean? This is the definition of divisibility. Divisibility where a divides c. And then when you end your proof, you put a little box here. Or you can write QED. I like the box rather than QED. So look, A divides C means what? That there exists some integer that when multiplied to A gives me C. And just by using these definitions of what does it mean for A divide B and for B divide C, we can combine them and end up with this conclusion. Okay, so that is a direct proof. So you just need to write it down about 40 or 50 times, and on the 51st time it makes sense. If you are a person who already understands it, well, aren't you nice? No, I'm just kidding. That's good. All right, let's look at, we've got about 5 minutes. What can I do in 5 minutes? It makes a little sense. Okay, good. It's better than if you said it makes little sense. Okay, so I think I must have to stop here because everything else that I want to do will take us like 20 minutes. Nothing to do. Okay. Yeah, so let's take a brain break. How about that? Let's take a brain break after this. Okay, so look, there is a learning curve, right? And it's a matter of becoming familiar with the fact we're doing math without numbers. But underlying all this is our same propositional logic. And the more you see it, the more familiar it gets, the more repetition you have, the more you free up space to understand what it means instead of just trying to figure out what you're even looking at. So that's it for now. We'll take a brain break, and then we'll come back on Tuesday and get back to it. All right. Any questions? How do you guys like this dry erase board set up on Zoom? How do you guys like it in the class, by the way? Yeah. Okay, you can. Oh yeah, yeah. It's hard to scroll back up. Yeah, yeah, I don't know. I like this too because I tend to want to fill up the boards and then start over. And that way you can get a whole picture of the thing. All right. Anybody else have a question on Zoom? Okay. Then y'all have a good weekend. I don't think there's any homework or anything you need to work on, but you might want to review the notes. Yeah. Rewatch, write down this proof until you understand it. It shouldn't take, I don't know how long it'll take, but if you keep writing it down, I know you will understand it. Right. Thank you for the talk earlier. Yeah, no problem, man. I want everyone to do their best. So you guys do your best to have a good weekend. Bye-bye.